Hey, hi, let's get started with Research Jam 13. I'll keep the intro short. I'm already keeping the intro short. Let's start with Dennis.
Hey everybody. I'm Dennis. I'm the machine learning lead at a startup called VoiceFlow. Today I wanted to share a little bit about multilingual tokenizers, so I can walk through that. All right. So I guess the context, we started using, so we've been training our own models internally for the past year and a half, and then we started experimenting more with some large language models when sort of the ChatGPT craze hit. And we've been using multilingual models, but we've been using the sort of standard Hugging Face transformer ones, the open source ones. So when we were implementing some of our models in a multilingual context, we found that there is significant token consumption for certain languages. So I wrote a little blog post about it and created a notebook for it. So I can walk through it and then share a little bit about how it impacts sort of the product side. I know this is more on the research side, but my background's more in industry, so I can sort of talk about the impact there. So I guess to start the story, I was going through sort of the GPT-3 playground and looking at different phrases, and what we had set up was a token limit for each of our requests. So we set it up at first to be around 256 tokens, but for certain requests across languages, it would break. We'd get incomplete requests. So I went through and started playing around with it. I thought maybe some of the requests had some weird tokens in them, but just going through with a fairly standard request here, like I want a pizza. In English, that's 4 tokens. In French, it's 7. And you can see it starts exploding for other languages. Chinese, it's 15, and Korean is 23. So this was kind of strange because the model can handle multiple languages, and I think that the tokenizer would be trained to be fairly balanced. But what I did was experiment with the massive data set, which is across 51 different languages, and tried to come up with an empirical result. So probably show it here, it's better resolution. So I tested across different tokenizers and found that the GPT tokenizer was probably the worst tokenizer for balancing English versus other languages. The OPT one is pretty bad too. So you can see here for English, for the data set, we had 88,000 tokens. But up here, I can never say this language correctly. It's an Indian language. It was over almost 1.4 million. So we have a 15, almost 16x difference here, which is very interesting because these are supposed to be multilingual models. But when I experimented for other open source models, so we had OPT was pretty bad too, but sort of the standard other open source models that I tried were actually pretty good at not having huge variance here. So this was part of the investigation, and I was trying to figure out like what the impact is. And it's, from an industry perspective, it's pretty interesting because usually tokens are the way we standardize and charge users for the model. So show quickly what we do in VoiceFlow. So when we create a project,
Dennis, can I ask a question about your plot before you move on?
Yeah, for sure.
So each one of these dots is an entire data set from a single language, right?
Yes, it's the massive data set per language.
And is it a direct translation of the same text in every language?
Yes.
So okay, that makes sense. So GPT-2 makes sense then. Something like the next one, so Roberta A base. How are there languages that have, it looks like, fewer tokens in that language than in English? That seems a little surprising unless the data set was actually more heavily biased toward, I guess, yeah.
Yeah, I think that's Chinese, I think, right?
Okay.
So that makes a little bit of sense. But yeah, it's an interesting development. I didn't go too deep into the specific tokenizers, but I know XLM Roberta has been fairly well used in industry. So
Mhm. That's
but
interesting.
yeah, same with BERT, right? We have BERT here, which had certain languages that were below English.
Yeah.
Um,
What's that first one in BERT base? Do you know it? Cage.
I don't know what that is. But
Cambodia.
there's probably additional variance here due to just the how compact a language is. 'Cause English might be more verbose. So yeah, it's pretty interesting, but I think it makes sense that English is near the bottom for all of them, but definitely interesting why for MT5 Japanese is down here, probably because the characters are more compact, same with Chinese. So
So what you're plotting is the entirety of tokens used in that language. Is it a vocabulary?
it's from the massive data set. So they have what is it, 20,000 utterances that they have across different domains. So I just use that as my base sort of.
Okay, so all the tokens used to encode that data set, which is different from your beginning example where you use the same sentence and see how many tokens each language uses to encode them. That's a different concept, right?
Well, they're supposed to be equivalent across every language. So it would be the, what is it, 18,000 utterances for English, and then those are gathered from the Slurp data set, then translated into French, translated into Spanish, then et cetera, et cetera.
Right. So, okay, my question is, if you given the same sentence, let's say English uses 9 tokens, French
Yeah.
uses 15, but some of them are repeating. And when you're plotting this plot, are you just calculating the unique tokens in that vocabulary, which will be less than 15 if they're.
Oh, I see. Okay. No, so I'm just tokenizing all of the sentences. I'm just running it through the tokenizer.
And then just see how long it is.
Yeah.
Are they fairly consistent across models? Like, is the top one always the same language? I'm sure not always, but like, is the correlation sort of high?
It's fairly high. It's usually the languages that are less common. Another plot down here. Yeah, so like a max min ratio between the most I guess compact language for the tokenizer and the least one. But yeah, usually English is closer to the bottom. It's interesting for these models. Chinese, for example, is closer to the bottom, but for GPT, it's closer to the top, or I guess in the middle-ish. So it varies quite a bit, but I haven't looked into specific, I guess, keeping them constant for a specific language and comparing beyond English.
It'd be interesting to look at, if you wanted to dig deeper in any of these, how many tokens in the tokenizer are from each language. Is it roughly the same, or you know?
Yeah.
Also, Sidesh, I think, has a question in the chat.
Yeah, so do you think these are related to the morphology of the languages? Because there is this type to token ratio, wherein like type to token ratio is number of forms a word takes divided by like number of words in the vocabulary. So I mean, for like, as you showed, for some of the languages, for English, the type to token ratio is very low because it is not that morphologically rich. Even Japanese is not. But there are some Indic languages and even some African languages which are very rich, wherein one word can take around 20 to 30 forms. So their number of tokens is expected to be more than English. So that was one consideration I think can be included. And second was like, if there is less data of language while training a tokenizer like sentence piece, then there would be there would be more number of tokens of that language in training. So I guess we need to look at the data set sizes that are used for training the tokenizer as well. I guess that statistic is there, that would be, I guess, helpful.
Yeah. For your first point, I'm not a linguist, so I probably understood around half of what you said. But I think that does make sense. Different languages express different, I guess, words, and it's more. I only speak 3 languages, so I don't know too much about African or even various Asian languages. For the second point, I think that was something that I was, I guess, assuming, just that the most common languages are most frequently occurring in the tokenizer, so they'll be better compressed.
I guess for MT5 tokenizer, what they have done is they have done sampling, like they have sampled each language like in same proportion. So that's why it shows more clustered, because I mean all sentences are shown equally.
Mhm.
All languages are shown equally.
Yeah, thanks for pointing that out. Definitely something to dig into.
So we're pretty much at 10 minutes now, but I guess questions have really been interspersed throughout this talk. So Dennis, do you want to keep going, but try to wrap up in maybe 3.5 minutes if you could?
Yeah, sure. I'm just going to do a quick demo on the impact, but I can just talk through it. Yeah, so I think towards the end, some of the things that, where is it here? That I talk about is we have an implication of cost and accessibility when certain languages are more poorly tokenized from a compression perspective, especially when a lot of APIs use it as a measurement. So just thinking about as we release more models beyond sort of the main, to call it 5 research languages in the world, just how that makes an impact. Yeah, and what the accessibility is there. So I think it was pretty interesting from our perspective. We had to adjust sort of how many tokens we can generate, but as a company, we do offer sort of a fixed amount regardless of language. So as we see usage sort of have an uptick, we'll try to track what the impact is across languages. I think that'll be pretty interesting beyond sort of an academic context too. So yeah, I guess we can take a couple more questions if there's time.
Yeah, we have a few more minutes. One question: why do you think the disparity will grow over time between English and non-English?
I think it's the more we use these models, the more money is being poured in, and the amount of capabilities increase. So when people are trying to sort of push the forefront in a certain technology, then I think there's a disadvantage to not using a technology. I think like the analogy is that if you're on a horse and then somebody else has a car, the car will go faster and faster because it's a better technology, and then people will try to, I guess, adapt it back to different conditions. So I think that's the concern there, is that there's a lot of excitement and hype and money and everything else being poured in. And I guess it's kind of researchers going back and adapting the models to other languages. But generally, for example, even finding data sets for other languages is quite a pain. Even in our space, it's a lot of it, like for some of our own training, we had to go and translate sort of using NLB or something else to another language. And there's obviously challenges there since it's not a native translation. So, right, I think we can wrap up there. Thanks everybody for your questions and comments. Gives me some more things to think about.
Awesome, Dennis. Thanks for presenting.
We have a room for you, Dennis, and on Discord. Hopefully you get to do a demo there. I'll be interested in checking out. Cool, let's move on to Charles.
Charles, right?
Yeah.
Okay, great. Thanks for letting me do this. Okay, I'm Charles Martin. I run a boutique consultancy called Calculation Consulting here in San Francisco. This is me. I'm going to present some work that I've done in joint with an old friend of mine at UC Berkeley, Michael Mahoney. I actually don't have a formal relationship with UC Berkeley, but I've known Mike for many years. We're both old theoretical chemists, and we've been working on this project it's been about 8 years now. So today I want to get some feedback on a paper we're trying to write called Semi-Empirical Theory of Learning. And I'm happy to share the paper. It's quite long. It's quite long. It's very pedagogic, but I'm going to present some of the key results here. And if anyone, and I'm happy to talk more about it in the Discord channel afterward, but this is essentially the point. I want to talk about some of the key empirical results that we've come up with, which we think will help justify a lot of the things that we're doing. The main idea of this is that we've been working for some time on a theory of learning, and it's encapsulated in an open source tool called Weight Watcher. This is an open source tool. We have almost 100,000 downloads now. And the way the tool works, for people who haven't seen it, is that it's a diagnostic tool, a data-free diagnostic tool for deep neural networks. You take your model, some sort of pre-trained or trained model, you look at the weight matrices, you do spectral analysis, and you analyze the histograms. And it turns out that this histogram of the eigenvalues, or the spectral density, can actually tell you quite a lot about how the model's generalizing. And so the tool is something you can use and download, and I encourage you to do that. And everything I'm going to talk today, well, within the tool. Now, this work is, the early forms of the work have been published in JAMLR. So we have a paper in JAMLR on implicit self-regularization deep learning. And we have a paper in Nature Communications where we've been able to predict the trends in state-of-the-art neural networks without access to training or test data. And I think this is probably the first paper that was a large-scale I actually think we're doing well because we can predict generalization. There was a talk this week about trying to develop a theory of generalization, and that's pretty much what we have here. And we're trying to really understand more of the fine-grained levels. Analyze a neural network and you look at the weight matrices. We believe that the weight matrices go through these 5+1 phases of training. You'll start off with a weight matrix. Most people initialize their weight matrices with some sort of random Gaussian matrix, something like this. And if you were to plot a histogram of the eigenvalues of that weight matrix, you would find that it fits this red curve very nicely, which is the Marchenko-Pasteur random matrix theory, which was actually developed in nuclear physics, for the Manhattan Project. So something And as you begin to train, you start seeing spikes pulling out. So you'll see near this edge, you see sort of these spikes will pull out. And as you do more training, more spikes sort of pull away from this edge and you get a nice boundary. But over a period of time, we find that the best trained models they're heavy-tailed. They don't look like a random matrix at all. They're heavy-tailed. And more importantly, you can fit the spectral density, again, the histogram of the eigenvalues, to a power law characterized by this exponent alpha. And we've looked at thousands of these matrices, maybe 10,000 at this point. And this is pretty consistent. There are going to be exceptions, but this is pretty, 80, 90% of the time, this is what's going on. In our JAMLR paper, we present these 5+1 phases of training appear as universality classes from random matrix theory. And we go through this, and the idea is that there are these different these universality classes. In our early paper, we sort of suggest is that the best fit models live within this heavy-tailed universality class. The best fit layers, the layers in the best models live within this heavy-tailed universality class. We suspect that layers that are in these universality classes are underfit. And we suspect, and we have some idea that layers that are too heavy-tailed may be overfit. But it turns out there's also something special we didn't talk about in the paper because there's so many details. There's also a special universality class at 2. So right when the exponent is 2, there's this special little universality class. I'm going to talk a little about why I think that's special. So these universality classes were developed also in theoretical physics for the study of complex systems, and they've been used quite a lot in quantitative finance. I used to be a quant at BlackRock. That's how I know about them. So generally, so far, what we've believed is that the best layers live in this fat-tailed universality class, and the closer the exponent is to 2, we think the better the layer generalizes. And we have some empirical data to show this. For example, if you look at a model like Albert, we can take a model like Albert, and if we look at we just measure this exponent for every layer, and we sort of take a very naive average of the alpha, we'll see that the average alpha correlates fairly well with generally some form of model quality. You pick, I just went to Hugging Face, downloaded these models, ran them through the tool, took the average model quality, you see you get a correlation. It's not perfect, there are exceptions, but generally speaking, we think we can treat coarse grain generalization quite well.
Hey, Charles, when
Yes.
you're making that
Go
plot,
ahead.
is the range shown the range over layers, or is that the range of the means?
No, it's our error estimate for alpha. So this range, which axis do you mean?
Yeah, the y-axis.
The y-axis is the average alpha, where you average the alpha exponent over all layers. So you just compute the parallel exponent for every layer and you take an average. And this is just basically some estimate of the error we think in the parallel estimator.
Okay.
And as we get higher quality models, yeah, so this would be like, you're right, it's the average over the layers, right? Of course, it's how this error bar is the error for this average.
It's the standard error.
Right. And as you find, as you get the higher quality models, that goes down, right? You have the models not only do they have smaller alpha exponents, but the range is also smaller, right? So they concentrate around this. That's a great question. Thank you. We also find that when you're trying to deal with models that are changing in depth, we found that you have to use or you have other types of scale anomalies. We find that sometimes there are scale anomalies that exist. And in our paper, we talk about this quite a bit, but basically there's a weighted average. You can take a weighted average of alpha where the weight is the log of the largest maximum eigenvalue, the scale, or the log spectral norm. And so if you take a weighted average, you get some of a slightly different metric. And we find that this can correct for a number of problems, issues that arise in depth, things that arise with Simpson's paradox. We have a number of papers where we describe this, but basically you have two metrics, either the naive average alpha or some sort of weighted average alpha hat. And the point is that in the paper, we can show that this metric alpha hat for a layer can be derived using techniques from statistical mechanics. So my background's in theoretical physics and chemistry. So when I did theory of learning back in the 90s, we didn't use VC theory, we used statistical mechanics. So I'm going to present this paper is a complete pedagogic derivation of this. And the key idea here is that, look, you can think of it as if I'm trying to measure, there's an old model called the student teacher model, which can give you the generalization error for a perceptron. So you have like a single layer, you can compute the generalization error of that layer. And that's simply done by considering sort of like a bootstrap model of how you would do the error. You basically look at given a model you have, some pre-trained model, you look at the weight matrix for each layer. You imagine you have some student which is trying to mimic the predictions of your model. And you average over all possible students that overlap with the teacher. And this is a well-known model in statistical mechanics. It's called the student teacher model. In our paper, what we do is we're going to take a matrix generalization of this. So instead of looking at a perceptron, we're going to look at we're going to actually use the fact that there's a matrix, not a vector. So we're going to form these correlation matrices where A is the student matrix and X is the teacher matrix. And we're going to look at the overlap, which is, J overlap W, which is going to look like W transpose AW. So we're going to average over this student teacher overlap. And the point is that if we take an average over all students, this will give us some estimate of the generalization error of a layer. So again, just very, very basic model from statistical mechanics from the early 90s. In our model, it turns out that alpha hat will then come out as something like a log alpha hat, which is alpha times the log lambda max, alpha times log spectral norm, will actually appear as like a log quality metric, where the quality metric is something like you might call like a log free energy or a log likelihood. In physics, this object is called an Zuber free energy. It comes from quantum field theory, quantum gravity. But the idea basically is you take an average over that overlap and you take log average of the exponential. So you see before, so basically you're applying Jensen's inequality. And so you're going to have this log overlap of this exponential where you're averaging over all student correlation matrices. And this gives you this form of this integral. These are called HCIZ integrals. And the trick to the Weight Watcher theory is that we know how to evaluate these integrals. Now, in order to evaluate this integral, though, you have to do a transformation. The key to this whole theory, or one of the keys, is you have to do a transformation from the measure over matrices to a measure. You have to take this measure over A, not the measure over J. So imagine that you have to take this transformation. You have to show that this transformation can actually be replaced with an integral over all square correlation matrices, where X is W transpose W. And in fact, in order to apply the theory, you have to assume that not only can you do this transformation, but this transformation can be restricted to some subspace of X, which I'll call X effective, which is defined by the tail of the spectral density, which is the whole point of our theory. So in order for this theory to work, you have to do this.
Hey,
Now,
Charles,
it turns out,
we're at 11 minutes.
yes,
Haven't had many questions yet, so we can go into the question time, but maybe can we wrap up in about 2.5, 3 minutes?
yes, the timing should be perfect. So here, the point is that you need to have the, you need to evaluate the Jacobian of this transformation. And so if you run the tool, the Jacobian means that the determinant of this effective operator should be 1. And what we find is that we believe that the theory is correct when the determinant of this effective matrix is 1 aligns with our previous theory, which gives us the start of the tail. And what we found is that when alpha equals 2, which in our theory gives rise to sort of what we call perfect learning, or the ideal part of our theory, where our theory predicts learning should be, you're going to find that the determinant does in fact align perfectly with the start of the tail. This turns out to empirically be true, not only in toy models, but it turns out to also work in models like Albert, which I showed you. In the layers where alpha is near 2, you see this overlap. And in models like VGG, which I showed you, where the layers have an alpha near 2, you also see this overlap. So again, this is all described in this new paper. And sort of I'll just end with a tweet from a friend of mine on Twitter who's a theoretical physicist, calculating something using entirely different techniques from different areas of mathematics and getting the same answer is lovely. And I think that's what we've done here. We have an older theory which predicts that when alpha equals 2, you should see the layer should be generalizing as best as possible. And now we have a new theory, which is using pure analytic techniques, where we derive this result and then we test it empirically, and we find that in fact in these state-of-the-art models we see this. So that's the talk, and I'll be on the Discord channel, and I'm happy to discuss in any more detail, share the paper with you, etc.
Cool.
And I'm open for questions if you have any.
I think we have, a minute and a half or so for questions. So I have one.
Okay.
Because this is a theory that analyzes layer-wise models, have you played around with like layer-wise either early stopping or tweaking learning as it progresses to optimize all layers kind of more independently? Like get
Yes,
and then stop, for example.
Yes, we're looking at that now. In fact, I think Chris is one of the fellows working with it. Chris is on the line. That's exactly what we're doing right now. There are some technical details in doing that, but that's exactly what we're trying to do.
Okay. And then second, for a given layer, besides just training it or stopping it, which is a pretty harsh cleaver, I guess, can you take a layer and otherwise modify it to keep the components that are closer to 2 and get rid of the rest, or to like mutate the layer?
Yeah, in the theory paper, we describe some experiments where we demonstrate that we can at least predict trends in a toy model by keeping the dominant components of the tail. Now there's some caveats to that, but yes, we have a long empirical section in the paper where we do just that.
By intervening to keep those components, you mean, right?
Well, we just remove everything that's not in the tail, and then we see how well we perform.
I see. Okay.
And in fact, you can do that with the tool. The Weight Watcher tool has a method called it's on the documentation also, but you can do it with the tool. You can actually take a pre-trained layer. You can just keep whatever, you can keep sort of the tail of the distribution. It will do an SVD transform back, and then you can test and see how well your predictions are.
Cool.
And I have one question. Do you think
Sure.
that, for example, while you're training, if you keep an eye on every single layer, and as the layer reaches the point, like you're like equilibrium point of 2, would it make sense to like freeze this layer and say like we reached the best learning like for this layer, and then basically like freeze this layer and do not like eventually like do this like early stopping layer by layer in a sense?
Yes, that's exactly what we're trying to do now.
Mhm.
There are some caveats to doing that because you have to actually have the layers have to form these parallel distributions. There are cases we've seen where there are scale anomalies that arise, and we're trying and we don't quite understand. Like for example, we know like if we train with very, very large learning rates, you'll see scale anomalies, and we have other things. We think maybe there may be some form that sometimes the layers overfit, and when the layers overfit, you can see scale anomalies would screw things up. So that's what we're trying to get to now. So I think that we understand at a coarse grain level what's happening with generalization, and we're now beginning to experiment with these very, very fine grain things. Again, there's a fellow on the channel, Chris, and maybe he'll join us on Colab and he can explain what he's been doing on that. But that's exactly what we're trying to figure out.
Cool. We're a bit over time, so we should probably move on with
Okay.
Alex, who
Okay,
is-
thanks a lot, guys.
yeah, thanks for presenting.
Yeah, 1 second, let me.
Share screen when you're ready, Alex.
Yep. Yeah, my presentation is much more applied. There will be not that much technical details there. But what I want to present here is the project I'm working on right now, and it is about running deep learning models in the browser with no like server side, no APIs, and anything, just straight up running in browser. So why I ended up doing this project? So when I was doing full stack deep learning course, I needed a cool final project for the course, and because of that I thought about like what stuff from what I'm working on right now can I use. And at the time I was helping my wife in her own research projects where she was working on these nanoparticles and microscopy images of them. And what we ended up doing, we trained sequoformer models up to like we made them very, very small, very tiny, like up to like 4 megabytes. Like the whole model is 4 megabytes, and this specific output is from these models. So we managed to train small models to give us very good results. And I thought about whether we can just like push these models like into the browser. And I ended up doing this, and it worked quite well. And then I thought about all the pain I had while doing this. So basically I had to perform everything we do in Python, and we have like a lot of nice tools for that. But I had to do all of that in JavaScript. And basically like reading the data, converting everything to specific tensors every single time, do all the pre-processing like cropping, normalizing, and everything in between. Then loading model, processing, post-processing, and giving up the like final result. So it is too much hassle, too much effort, and especially it was painful for me. But I work as an AI engineer, so I have knowledge of why we do it this way and how to do it this way and how to do it like more or less proper way. But people who are not specialists in that, who do primarily like web development, it would be like too much pain for them. And because of that, I think people are quite hesitant to using more deep learning in web projects. So essentially what I ended up doing, I encapsulated everything, like all pre-processing, post-processing, and running the model into the model and into the library. And what you can do as a web developer, you can just like create the model with one line of code, then process with another line of code, and that's it. You have your like final result, whatever it is. Whether it is text model, whether it is image model, like whatever, it works in like 2-3 lines of code, and you get your result in the format you like can work with right away. So whether it is like text, you get back text. If it is image, you get back image or numeric vector, which again, you understand how to process. So it is not something like you don't not get like some abstract like tensor of whatever dimensions. If you want to extract features, you get a list of features, and it is kind of straightforward what you can do with them. And how it works right now, so I run OwnNX for web for this, and I essentially adopted the Hugging Face format for the models to do all the pre-processing and post-processing and all the stuff in between. And what I was very surprised to learn is that you can compress the models very efficiently. So in some cases, you can compress models more than 2 times to minimize the traffic and the amount of data you store in some remote storage. But not like it is not ideal thing at the moment, at least. So what challenges did I encounter? So it is not that easy to use GPUs in browser, and it is hard to implement everything from scratch. So no matter what is the use case, you have to do like everything from the very beginning. And what I would like to know, like essentially why I'm here. So what are potential use cases for that? So for example, what can you imagine be useful if you were starting some project for web development? So, and obviously it is better to see than just to hear. And I want to also go through a quick demo how it works right now. So here you have the site, and on the site there are a bunch of demos for image and text models, so there is not that much at the moment. And like the models work quite well, quite fast, so you can just load the image, and there is no, like as I said, there is no like backend or whatever for this, so your images stay on your computer, so they are not being sent anywhere. And for like, for example, you can even just compare images, say like, for example, like 2 images of New York are very similar one to another, and if you compare it with image of Pug, they're obviously like very not similar one to another, but if you add another Pug on the other end, you can get very high score for that. So, and this thing uses all the open source models. So basically right now what I do, I take some nice interesting models from Hugging Face Hub. Then I use like standard tools from PyTorch to convert it to OwnNX and just upload it to some remote storage. Yeah.
Can I ask the resolution?
Basically, you can load whatever resolution you have. Inside, they will be like converted and compressed to whatever model uses. For example, you can like upload the image of 2000 by 2000, but if the model works with the image of size like 224 by 224, it will be resized to this side.
Yeah, can I see a demo of super resolution?
Oh, super resolution. Yeah, I can start, but super resolution is like very, very slow.
I see.
Yeah, it can do like 4x super resolution. And 1 second. Let me. So, but I have a bunch of actual like examples, so how it works in the end. Let me just share the. 1 second, I will switch to. Yeah, for example, for some images, it works really well. So from this low resolution image, you can go to this fine-grained image, but so this particular model, it adds like some, so it is not that realistic, I would say. So for example, it creates like more artistic or cartoonish vibe for the images. So it is not like photorealistic. Yeah, but anyway, like the actual results are pretty nice. So they look nice, but it is not for all the use cases, I would say. Yeah.
Maybe I missed this earlier, but so this is CPU only. What
Yes.
libraries are you using to do the actual like linear algebra?
It is ONNX.
Okay, which already works well in the browser. Like, is it pretty optimized, at least for CPU?
It is pretty optimized. So recently, TensorFlow developers, they are also working. So they have much more like they have TensorFlow.js with more functionality than ONNX at the moment. And they have WebGL support and WebGL 2 support, and they're working on WebGPU support. And recently they released their set of pre-trained models for somewhat similar tasks. And I compared the performance, it is like on a par with that models. So even when using CPU, it is not that slow. As you saw, for example, smaller classification models, they run in a vicinity of like 50 to 100 milliseconds.
And you're saying that's roughly the same speed I would get if I compiled PyTorch on my local machine, CPU only, and ran it that way?
No, I would say like PyTorch, even on CPU, it contains more optimizations. So it should be like, I would say it should be faster, even on CPU, but through like PyTorch, C++, I would say that running stuff in browser is slower, but it is still bearable. So it is not that critical.
Okay.
Yeah, and I will also share if we have time, I can show a couple of more demos.
We have a couple more minutes. We're at 12 and a half, so we should finish up in about 2 minutes. One random idea you could have, obviously you can have people running their own models, using their webcam, inputting pictures and stuff, as you've shown. One random idea would be you could have like instantly created, massively parallel like clusters where people all just go to a website. If you had a million people go to a website, then they would be put into an instant cluster and used to train some big model.
Yeah.
Like,
yeah.
You guys
yeah,
wanna see something. I need help for my iClear deadline, and like all these people use their CPU only, sadly, but like massively train some model together.
Yeah, actually, it is not that crazy idea because I already thought about it, but not for training, but for inference. For example, if you have like very huge model, you can actually like using built-in tools, you can dissect it into much smaller models, and then you just distribute these models across multiple just browsers, and people wouldn't need to install like anything. You can just go to this website and you will be automatically a part of large inference cluster. So yeah, it is implementable. So I already played with it and it can be done, but it will be like a lot of effort to actually pull out.
Cool. Should wrap up in about 1 minute. Anyone else have any questions? Or Alex, you're welcome to show, one more.
Okay. Yeah.
If you have one.
Sure. Yeah, for example, like I showed image, and here is, for example, summarization. Demo. So you can put very large text and it can run sort of real-time streaming summarization of the text. And yeah. So again, it depends on the model. Some models are better, some models are worse in summarizing, but anyway, it quite well summarized these several abstracts about nuclear fusion into one smaller text. And for example, if you go like and try to summarize longer paragraph into smaller text, like this is the default behavior for summarization models. Often they just take one like first sentence and they just output it as a summary for that. And one last example, which I essentially started with. So it is a grammar correction. So you may have sort of like offline version of Grammarly for your use cases. So as you can see here, like from basically this is what Grammarly thinks about this sentence, and the very same result can be achieved like fully offline without any without sending your text anywhere. Yeah.
Awesome. We're at time. We should wrap up.
Sure.
Thanks for presenting. This is really interesting, and I hope it makes its way out there into the world. People find something cool to use it for. Last person, Thomas, you're there. Good to see you. Feel free to present.
Right. So this is going to be even simpler than the previous one. It's just a way to generate a lot of meta learning tasks. Like I'm interested in meta learning, in meta reinforcement learning in particular. And for various reasons, I would like to generate a lot of tasks. So I just found a way to do it. Quite simple, but reasonably effective for my purposes. So the general idea of meta learning, for those who are not too familiar with it, it's not really complicated. You have a certain type of environment such that to solve each new problem in the environment, the agent must do some kind of learning. And you want to generate some agents which are very, very good at it, which can learn very fast in each new case or each new situation in the environment, as opposed to having to train them over thousands and thousands of episodes every time. For example, you could have bandit tasks, like with 2 arms, and you need to find out which one is the one that gives the better returns. And so the way to do that is for each new bandit, you have to try and learn which one is the best one from rewards. Or you could have maze tasks, where you have a certain type of mazes, and for each maze, you must find out where the exit is. Or you could have quite a different type of environments, each of which require some learning to solve each new instance of the task. Yes, so the way it's done in general is very simple. You have your agent, you take one specific case, one specific task within the environment, for example, one specific maze, one specific bandit, one specific pair of objects for the Hello task, etc. Well, one specific type of task. You train the agent to solve this problem. That's the inner loop, like each episode, each single individual task is one inner loop of learning. And you repeat that over many different cases, like many different mazes, many different bandits, etc. And between the episodes, you optimize the agent somehow to get better and better at performing this general type of task. Many ways to do it, many type of examples. So there's a lot of research on that, a lot of very interesting papers. But one thing is that the total number of environments that are being used in those papers is quite limited. I mean, you need to find environments which require some reinforcement learning, but which are not too hard or and don't take too long, because otherwise you cannot do the outer loop. So that poses some constraints. And most papers on this subject tend to use a small number of different meta tasks, different, it's difficult here, but different environments. So for something I wanted to do, I thought it would be nice to have a large number of different meta tasks of different environments. And so one way to do that is to randomly generate them. But the thing is to randomly generate meta tasks, not individual tasks, but meta tasks, you need to find a certain space, a certain parameterization that covers a wide range of possible meta tasks, and which you can explore by varying the values of the parameters. And this parameterization should be as simple as possible, so you can keep exploring it, but not too simple. It should be complex and variable enough that it should at least cover a certain range of existing meta tasks, things that people actually use in literature papers. So that's pretty much what I did. I came up with a simple parameterized space for meta-learning tasks, for simple meta-reinforcement learning tasks. The parameterization in itself, it's in text, but the advantage is it can be represented very easily graphically in terms of states. It looks a lot like an MDP with some variable components in it. The convention here, I don't know if it's easy to read, especially on small screens, but the tasks are organized in a series of states, like an MDP, but they're actually partially observable, which means that the agent doesn't know which state it's in. It has to infer it. And so for each state, there are some possible actions which lead to different states and possibly to some rewards. There can be a certain observation, a stimulus, which may or may not be provided for each individual state. And there are some rules to determine when the agent gets a reward. So for example, when this agent is in state 1 and takes action 0, it gets a reward, or when it's state 2 with a probability 0.2, etc. Okay. So if I had just defined that, I would have essentially, one single task. If I just define, for example, a kind of graph like this, I have a single task. The agent gets in a state and it needs to determine for each state which decision to take in order to maximize its rewards. The way to turn that into a meta task, into a distribution of individual tasks, is to have some components of the system to be variable, to be resampled anew from a certain distribution every time you generate a new task from this meta task. And here it's very simple. Everything that's variable is in red. If it's in red, it's variable. It's resampled anew for each new individual task. If it's not in red, it's fixed. It's the same across all instances of the meta task.
Hey, Thomas, why not make the transitions also resamplable?
You could. There are ways to do that. It turns out that I didn't need to do that. As I'm going to show, even if you don't do that, you still have a space that's large enough to express pretty much all the tasks that are commonly used, at least the simple ones, in meta-learning papers. Okay. But you definitely can. It's just that I don't need to do it. Okay, so that's a bit of a complicated example. I'm going to show this one, which is much simpler. That's a simple 2-arm bandit meta task. That is the bandit task as a meta reinforcement learning environment. It's the simple, possibly the simplest possible one. You just have one state and you have 2 actions, the 2 arms of the bandits. And each of these arms gives you a certain reward with a certain probability. And the probability for each arm is resampled for every new instance of the task. So when you generate a task from this environment, you initialize both probabilities to a certain value. And then the agent is dropped into this state and must take actions repeatedly, every time coming back to the same state. And from that, since the reward rules determine it gets an action, a reward for action 0 with probability P0 and a reward for action 1 with probability P1, and must somehow determine which one is the best one. In other words, it must do a very simple form of reinforcement learning. And with this specification, with the probabilities being variable across tasks, you have basically the specification of a bandit meta task, the simplest possible one with 2 arms. And there's no stimulus or observation, just 2 actions with variable probabilities. That's the simplest one. There's a slightly more complicated one here, which is the so-called Harlow task. The Harlow task is when it presents you 2 objects, and one of them contains food and the other doesn't. And so you must pick one. And then I present you those 2 objects again, and again you must pick one, etc., 6 times for each episode. And then that's one episode, and in the next episode I do the exact same thing, but with 2 completely different objects. So every time you have 2 objects, and you must determine by trial and error which of them contains the food. What happens is when you do that with Monkey, initially they're pretty bad, like they will need many trials to find out which of the objects are the food. But after they understand the overall meta task, the overall structure of the problem, eventually they just did 1 trial to determine exactly which one has the food. Like if this one didn't have the food, then I pick the next one, and this one had the food, I keep picking the same. So it's the original meta learning task, at least in the actual neuroscience literature, and it's commonly used in papers. So here is described again pretty easily. The initial state is always state 0. And you are repeatedly shown 2 objects. When there is a bifurcation, it means the 2 outcomes are equal probability. It's one of them. And since there is no action specified here, it means whatever actions you take is the exact same results. You're going to see one of those 2 actions, one of those 2 states with probability 0.5. And so action 1 means, I think, yes, action 1 means pick, and action 0 means don't pick. And the reward rules specify, well, that's the opposite. Action 0 means pick, and actions 1 means somehow. Yeah, don't pick. Actually, state 1 is the rewarded object, the one that contains the food, and state 2 is the one that does not contain the food. And so every time you pick an object or don't pick, you still get to either the same object or the next one with equal probability. But the rewards are different. The reward depends on which state you're in and which action you take. And for each new episode of the task, you randomly change the observation provided by each state. That is the identity of each object. And so just from the rewards that it gets, the agent must determine which of the 2 objects it sees is actually the rewarded one, and which one it should keep picking. So simple Harlow task, which again is a canonical task in meta-learning literature, again implemented pretty easily.
Thomas, we're at 12 minutes, so we can go to questions into the question time, but we should wrap up in about 2 minutes.
Sure. But basically I'm done. It's just to express that here I have a simple specification which can determine a lot of simple meta tasks. This is a T-maze, a maze where you have to determine whether you go to the right or to the left at the end, depending on the nature of 2 stimuli that you see. But basically you can have a lot of them. And importantly, you can generate random ones. That's the only reason to do this, really. Like, those are randomly generated meta tasks in various forms. And this one is also randomly generated, but it turns out that accidentally it does implement a common type of meta task in literature, the K-door task, where you need to go to the door, but first you need to pick the key in order to open the door. And the key can be in any of the states, and so you need to find which of the states is the key. So that's it, pretty much. There's a GitHub somewhere. I can give a link in the chat later, but yeah, there's code to generate as many meta-learning tasks as you like, including occasionally some interesting ones. So yeah, that's it. Thank you.
Cool. Thanks for presenting. Any questions for Thomas?
Can I ask, how do you see the relationship between curriculum learning and meta RL in this context? Do you see it as a spectrum, or do you see it as a totally different thing?
That's curriculum learning can be a part of meta learning, and you could even design the curriculum in the outer loop, like since each individual instance requires some learning, possibly over many trials. You could imagine that as part of the meta task specification, you could have a curriculum for each new instance of the task. Like, for example, for the maze are a bit, and you could have curriculum at both levels of the meta task. I think it's orthogonal. Basically, you can use one with the other or not, depending on how you like, and you can use it at both levels. But yeah, you could use meta learning to design a curriculum for your environment. If you had a specification for the curriculum, which could be parameterized and optimized in the outer loop. So you could use it.
Which reminds me of some work where there's like an agent that's trying to design environments that is the perfect next environment for the agent to learn either the meta task or the curriculum.
You could try that. Yeah, you could definitely try that. I think some people do that. But
Thank you.
no problem.
We're at 15. We should probably wrap up. Let's all take a moment to thank Thomas and all the other presenters for some great presentations. Roseanne, any last words? And also let me paste into the chat a link for the Discord.
No, we have rooms ready on Discord, so feel free to engage there. And yeah, nothing. Submit to future research jams, showcase your work, and also get feedback, get connections, start conversation.
Could I ask you? I'm sorry.
Mhm.
Could I ask a brief question? I'm aspiring, like, I want to be able to publish research. Would be my first paper, and I'm looking for where should I ask about guidance on, like, I'm looking for guides on how to write a good paper, how to do good experiments. Where should I ask about that stuff?
Discord would be the place to ask generic questions like that. And
Okay.
And I'm sure people would be sharing articles they found and they read that are in that direction.
Also,
Awesome,
Robert,
thank you.
you're welcome to show up here and present, the broad topic you're interested in, as well as 2 or 3 paper ideas, and just ask all of us on this call, like, hey, do you think any of these are publishable or worth working on?
Oh, cool.
Very appropriate here.
Thanks so much.
All right, see you guys all over on Discord. Underneath the research jam heading, there are 4 rooms for Dennis, Charles, Alex, and Thomas. So we'll be in there. Feel free to stop by and ask the authors anything. And for all of the presenters, please show up to your own room.
Thank you.
See ya.
Thanks a lot, guys.
Thank you.
Bye.
Coming.